It turns out that the microscopic physics
Mhm.
is better described if we say there is this teeny, indivisible thing at the bottom of it all.
Yeah.
And the mathematics that describes that indivisible, teeny thing that has turned out to be remarkably accurate is called quantum mechanics.
Hi, I'm Dr. Emily DeJeu, host of Tepper Perspectives. If you've been enjoying this content, we hope that you'll comment, like, and subscribe. Picture this. You wake up in the morning and check your phone to see the weather, maybe news headlines before work. You start your programmable coffee maker, turn on your electric toothbrush, and open a map application on your phone that uses satellites miles above the Earth to route you around congestion in real time. Maybe on your commute, you stream music or a podcast from a device that fits in your pocket but contains more computing power than entire research laboratories once did. Now, none of this feels extraordinary, but a century ago, nearly all of it would have sounded like science fiction. Your morning routine and mine are possible today because decades ago, scientists discovered that at the tiny scale of atoms and subatomic particles, matter behaves in ways that defy intuition. Those discoveries transform modern life so completely that most of us now move through a world built on physics that we do not understand and rarely, if ever, think about. Now, researchers think we may be standing at the edge of another physics-related transformation, one that could reshape computing, energy, communication, medicine, and infrastructure all over again. Today, I'm speaking with Dr. Sridhar Tayur, the Ford Distinguished Research Chair and University Professor of Operations Management at Carnegie Mellon University's Tepper School of Business. In 2018, Dr. Tayur also founded the Quantum Technology Group at CMU to look at business and other applications of the second quantum revolution. We'll put a link to the website in the show notes. For now, the interview. Dr. Sridhar Tayur, welcome.
I'm here.
And we're glad you're here. We're glad you stopped by. Okay, so we're talking about things that are technical. It's going to require people to dig back in their brains to think about physics. So I want to start with a level set.
Okay.
When people hear the word quantum, it can sound abstract. It can sound futuristic. In simple terms, what is quantum mechanics actually describing?
Okay, so I don't know why people are afraid of the word quantum because it comes from the same root, Latin root, quantus, which is quantity,
Okay.
right? Is anybody afraid of the word quantity?
Easy.
It's how much,
Right.
right? So quantum is this indivisible, tiny bit.
Yeah.
That's it.
Yeah.
Okay. Now you say, why is that important? It turns out that the microscopic physics
Mhm.
is better described if we say there is this teeny indivisible thing at the bottom of it all.
Yeah.
And the mathematics that describes that indivisible teeny thing that has turned out to be remarkably accurate is called quantum mechanics.
Got it.
So it is just the math of what we believe is the indivisible kind of the bottom.
The math of extremely small
Yeah,
things.
that have nothing smaller than it.
Yeah. Okay. Okay. So I like that. That's accessible.
That's what it is.
People can get their minds around that. All right. So this math of extremely tiny things that are at the bottom, indivisible, can't get smaller. In the 20th century, your work describes, and I think your work helpfully gives people a little bit of a history lesson because we don't necessarily think about how the technology we enjoy every day came to be.
Yes.
But you talk about how in the 20th century, we had this first quantum revolution. What was that revolution exactly, and how did it impact life as we know it today, sitting here in the 21st century?
Yeah, so laser pointers, we all use it in class. We use it in presentations. Who's afraid of laser pointers?
Right.
Nobody, right? But if you say, what is the mathematics that describes all of those, red beams or the blue beam, that's quantum mechanics.
Got it.
So similarly, all of us use smartphones. So we are used to, just typing stuff and stuff happens. So obviously, there's an integrated chip, which means it has billions of something called transistors. And the math of the transistors is quantum mechanics. So we've been using things that has quantum mechanics underneath it for 100 years. So one way to think about it is you might not know that you're using quantum mechanics over the next 100 years, and you don't have to know it.
Yeah, I think most people don't.
Right. So if you think about the billions and billions of transistors that are there in the integrated circuit that is inside your smartphone, that's all quantum mechanics.
Yeah.
Right. So whenever people take Instagram photos, the digital camera, right, it has its basis from quantum mechanics, right?
Yeah.
So less, I guess, pleasant is when people are asked to go get an MRI, right? I mean, we don't,
Yeah.
we don't get MRI for the fun of it, but
Yeah.
but you say, okay, if I have to do it, I'll do it. But the technology that is based on the mathematics underneath it is also quantum mechanics.
Yeah.
So I think we are already used to quantum mechanics at the consumer level. We are used to quantum mechanics at the medical imaging
Yeah.
level. We're used to quantum mechanics at the fun imaging level, and so on and so forth. So I don't see why people should be afraid of quantum mechanics at all.
Yeah. Especially because you're making the case it underlies much of the technology we take for granted, even though we don't understand necessarily that it's quantum mechanics powering these devices,
That's
right? Or
correct.
making these particular breakthroughs possible, that we just think this is how a phone works or this is how medical imaging happens.
That's right.
Yeah.
Yeah.
Okay. I like that. So your work, now we've talked about what is quantum mechanics, this first revolution, like you've said, right? A century of things being built sort of on the basis of quantum mechanics. Your work explores what you called a second quantum revolution. I'm curious, what is that? How does it differ from the first, where we were already sort of building technologies based on quantum mechanics?
Yeah, good. So I think some of these names come kind of after the fact, right? So when people were inventing the transistor, I don't know whether they were thinking integrated circuits, they were thinking smartphones, right? And somebody else at MIT was, inventing the laser, right? And I would say from maybe the 1940s to about the 1980s, a lot of these technologies, got commercialized. They became part of our infrastructure and so on and so forth.
Yeah.
And looking back, somebody said maybe we should call all of that the first quantum revolution.
Yeah.
And so at the time when people called it the first quantum revolution, they were already thinking, what else can we do with quantum mechanics that we haven't done? So let's think of it as this way. Quantum mechanics has a bunch of different features. We have taken a few of those and built technologies that are part of the first quantum revolution.
Yeah.
There are features of quantum mechanics that have been known since the 1950s, 1960s, or even earlier than that, 1940s, that we haven't put together into technologies.
Okay.
It's not as if something called entanglement is new or something called superposition is new. It has been there, I would say, almost since the 1930s and 1940s.
Okay.
What people started thinking around 1980s and 1990s is, are there other pieces of quantum mechanics that we haven't used that we can use to make computers work differently and therefore faster?
Okay.
Can we use different aspects of quantum mechanics to capture images that are simply out of reach of what we're doing right now? Can we communicate information across fiber optics in a way that is more secure than what we're doing now?
Do you think, so you mentioned like entanglement, superposition. I think my understanding is these just are descriptions of these tiny, right? No longer indivisible, absolute bedrock, that these these little things, they behave in ways that are not predictable and can be difficult to harness. And that the first quantum revolution, we're sort of building maybe in an aggregate understanding of how this works. But are you saying that now we're able to drill down into some of these features that perhaps 60, 70 years ago were just beyond our capabilities to harness, and now we can actually do something with this knowledge that's been known, but maybe to date hasn't been accessible or harnessable?
Yeah, so it's almost like this. I don't think we can do what we want to do in the second quantum revolution without having the machinery and the tools and the understanding that came out of the first quantum revolution. So it's almost like you can't get a PhD without having finished your undergrad.
Gotcha. Yeah.
Right. So think of it as you finished undergrad, and now you're like, you know what, I like this. I want to get a PhD. So you're getting more into it. But you're right. What physicists and engineers did with the early understanding of quantum mechanics is sometimes they use the word, we used bulk properties of quantum mechanics. I think that's what you're referring to in your question, and not really the individual properties of the teeny weeny thing. So this teeny weeny thing is supposed to not exist in a definite state unless you measure it, or until you measure it. Okay, that's like saying this cup doesn't exist as a cup unless I'm looking at it. Okay, and these are some of the philosophical questions and problems that even Einstein had. He said, if I'm not looking at the moon, is the moon not there? And does the moon show up only when I look at the moon? So he wasn't really, in a very strange way, he was a founder of quantum mechanics. He understood quantum mechanics so well that he didn't like it. Right? But today understanding is, you know what, things look definite to us in this classical form. But if you dig in and you look at an atom and you look at the electron and you get deeper and deeper, that thingy, which we cannot see with our eyes, is actually not in a definite position unless we measure it. So if it's not in a definite position, it is in some indefinite position, which means it's in a superposition. Right? It is either left or right. Let's put it that way. So that's what the superposition means. Right? Entanglement is even trickier than that, which Einstein really hated. He really couldn't get himself to admit that such a thing is possible. So entanglement means that A and B are so tightly connected that they are actually the same thing. Right? So we call them A and B, but they're so entangled that if you do something to A, you are automatically doing something to B.
I see.
That itself is not too troubling. You say, well, what's wrong with that? But what happens in quantum mechanics is you can be doing something in A in this part of the universe, and in some other part of the universe that is 5 light years away. If you turn this left, that dude will turn right instantly. And Einstein didn't like this, and they called it spooky action at a distance.
It is a little spooky sounding.
It's spooky. And he created a lot of experiments to disprove it. Anyway, long story short, starting around the late 1960s through about the 1980s, experimental physicists tried to see if entanglement is a true physical phenomena or is it just a mathematical artifact. Right? And then the 2022 Nobel Prize in Physics went to 3 experimentalists for physically demonstrating that entanglement is a physical phenomena in our universe.
Interesting.
You see?
Okay.
So I think this is one of 2 or 3 examples where Einstein would be rolling
Yeah.
in his grave saying, I can't believe God made the universe like this.
You've explained it well, given that it's spooky and weird and, troubled Einstein. You've explained it quite well. So thank you for that. Something interesting about your work, and I don't know if this is unique to you, but it sounds a little bit like this is the way you conceptualize it, is the second quantum revolution is about physics, but it's not just a physics problem. You make the case this is also about optimization, it's statistics, it's uncertainty, and decision-making under uncertainty. Why are fields like operations research, data science so important when really what we're thinking about is a large set of physics questions?
Yeah, so I think part of the issue about optimization is it's always been there. For example, if you're trying to design a product, you want to get the best functionality at the lowest cost. I mean, that's optimization, right? Now, you want to achieve a certain amount of fidelity, in your images, but you want to use the least amount of computing power, right? So once you start thinking about building a product, bringing a product to market at a cost that is market compatible, it's no longer just physics. Right?
Yeah.
It boils down to making choices on quality of the product, right?
Yeah.
And where you manufacture it, how you manufacture it, right? And so all products, I think, have this underlying decision making and optimization built in. And so for that reason, there's no reason to believe that real products in the second quantum revolution will not also have all those features.
Yeah.
What makes, I think, the second quantum revolution even more, in some sense, fun for optimizers and operations researchers to do is this optimization is not just at, let's say, the post manufacturing or the manufacturing design or sales, right, and supply chain level. I think the engineering challenges that the second quantum revolution is facing today, even in the fundamentally designing what it is that you will manufacture, is requiring us to be very, very careful in how do we manage the uncertainty that's inherent in this quantum system and how to design it with a predictable performance. So in some sense, we are doing the optimization of the engineering physics also.
Not just the manufacture and distribution of a product.
The product.
Yeah. And is that uncertainty inherent in there? It sounds like that uncertainty, because we're drilling down to these individual behaviors of these teeny tiny things that themselves behave in ways that seem to defy logic. Is that where that uncertainty comes from?
Yeah. So not only is there a indivisible teeny weeny thing that you can't go any more under, manipulating that teeny weeny thing leads to unpredictable outcomes.
Right.
So the underlying epistemology of, if you want to call epistemology of quantum mechanics, is that residual uncertainty.
Yeah.
Okay. And so you have to manage that. But then there's a practical aspect of it. There is no perfect device. So devices are themselves going to have imperfections, and they're going to be noise because they're constructed out of imperfect things. So there are two levels of uncertainty. There is the fundamental uncertainty that we believe is how quantum mechanics works.
Right.
But then there is a reality of the fact that whatever device we build, we are building using imperfect machines and things of that type. So both those levels of uncertainties really come together in far more, let's say, intrinsic way in the second quantum revolution than it came about in the first.
It sounds like it, and will keep you in a job for
Not only that, even in the first quantum revolution, you might not know this, but to design an integrated chip, it's a pretty serious optimization. And that optimization requires a solution of traveling salesman problems and all the kinds of stuff that our OR professors have been doing for the last 40, 50 years.
Yeah.
I think, so a lot of the stuff that you're asking, isn't it just physics? It has never been just physics.
Yeah. So let's again, your descriptions are helpful, and if we make this even more concrete, let's say we're at the kind of the threshold of the second quantum revolution. What kinds of real world problems that we would experience, the audience would experience, are difficult or maybe impossible for classical systems to solve today, but could potentially become manageable through second revolution kinds of quantum technologies?
So the holy grail of understanding, let's say, our chemistry
Mm-hmm.
is to work at a model that is microscopic.
Yeah.
Because putting even 20 of these microscopic things together and understanding how it works is so difficult.
Yeah.
People today have very crude
Yeah.
approximations
Yeah.
for it. So if you ask a pure scientist, they will readily admit that they're either solving very, very tiny problems at
Mhm.
microscopic level, or they are solving medium size at a crude level.
Got it. Yeah.
So they are looking for the second quantum revolution with respect to quantum computing just to do better science at the fundamental level.
Yeah. Okay.
Okay, so their excitement is of one type,
Yeah.
right? And they believe that there are mysteries of the universe that we still don't know,
Mm-hmm.
right? And what we know of quantum mechanics and so on and so forth is based on using our crude tools.
Yeah.
But imagine if you can start digging deeper, poking around, seeing the interactions. How do you know that you won't see new phenomena that you have not been able to see? So I think there's a lot of excitement from folks who are looking to understand more fundamentally how does our nature work.
Right.
Now, I'm in a business school, so
Let's get to commerce.
which is more like show me the money,
Sure,
like
sure, sure.
and soon.
Yeah.
Right. And so sometimes when I give a talk and I'm the only business school professor, I use the Jerry Maguire, kind of a
Yeah.
quote, right? Show me the money. Right. And so then you say, what are practical problems that can benefit from some progress in second quantum revolution?
Yeah.
Right. So I've done projects with the hedge fund in New York.
Mm-hmm.
Obviously, they use a lot of computing power to do machine learning. They do a lot of computing power to figure out various strategies of investments. But they're all based on a certain formulation and approximation of kind of the world that they have,
Right.
and using the GPU clusters
Yeah.
and so on and so forth. So we took one of their problems and said, if you had a quantum computer, how would you design the algorithm differently?
Mm-hmm.
But then we don't have a quantum computer, so we can't really solve it on a
Yeah.
quantum computer. But we can solve it on something called a quantum inspired computer.
Okay.
Which means that it's a specially designed computer that is to mimic what a quantum computer looks like, but using the technologies that we already have.
Okay.
So it's not the full thing, but
Mhm.
it's like a step towards it.
Yeah.
So using that quantum inspired computing, we use the new
Yeah.
formulation, and we showed that it is going to be 5 to 10 times faster than what they're doing with the GPU cluster.
Got it.
Or they can get answers that they were not getting before. So it's not like 1,000 times faster,
Mm-hmm.
but they will take 5 times faster.
Yeah.
Right?
So faster, better answers, less compute, perhaps.
So you're getting faster answer right now because the first generation of even the quantum inspired computing, we use GPUs and CPUs.
Yeah.
Okay. So the energy savings, were limited.
Mm-hmm.
But now new ideas have come up where you say, I don't want to use GPUs or I don't want to use CPUs if I
Mhm.
can. Really, what happens at a very basic level is the CPUs and GPUs, these are called digital architectures. And what that means is you take something that's analog, which is, um, uh, uh, how nature is closer to,
Mhm.
and then you make it crude.
Okay.
You make something like anything below 0.1, we'll call it a 0. Anything above 0.7, we'll call it a 1. And we'll create a lot of redundancies so that when we call it a 1, it's like really a 1. And when we call something as a 0, it's like really a 0. And so that's how the digital transistor integrated circuit work.
Yeah.
Okay. So it's very fast compared to hand calculations.
Right.
But every engineer knows that there's a lot of energy and time wasted because of this digitization and redundancy. Okay. So now people are trying to say, do I need it to be digital, or can I do more analog computation? And there what happens is you get much more energy savings.
Oh, okay.
So I think there is classical, there is CPU, GPU, there's quantum inspired based on CPU, GPU. Now we're going to say quantum inspired based on some analog devices.
Yeah.
Right? So we are getting faster, less energy, more faster, less energy, and kind of like a ladder
scaling
towards
from there. Yeah,
scaling
that
from
makes a lot
there.
of sense. So you there's a couple major areas that you explore in your work. You've mentioned one, quantum computing is one, quantum sensing is another, quantum communication is a third. Those are sort of three buckets I found reading the papers.
That's correct.
Which do you think ordinary people are most likely to encounter first in their everyday lives? And where do you see, maybe, I guess related, the most meaningful practical applications emerge for people out of those groups I just named?
So first, it depends on who you ask, from what I understand. I was at a workshop just last week in Washington, D.C., at the National Academy of Engineering, in a kind of a building. And when I presented my talk, some people were really excited that I highlighted quantum sensing as an example of a near-term application in, let's say, identifying gas leaks in pipelines, using something called LiDAR, and and so on and so forth. And some professors, I think they were from Purdue and others, leapt out of their chair and felt that quantum computing was getting too much airtime. And quantum sensing is where to go, right?
Yeah.
Just after that person said that, a person jumped up from the front row and said, nah, let me stop it right there. So what I'm saying is the engineers who are working the second quantum revolutions themselves cannot agree. Okay, so now I'm a business school guy trying to figure out what it is that these folks are saying. So
caveats made.
Right. So I created a quantum readiness ladder kind of a thing. Okay. So there are 4 levels. Is the first level, which is, do you understand the mathematics of it, and can you simulate the mathematics on a computer?
Yeah.
Can you do that?
Yeah.
Right. That's more like a PhD postdoc kind of work.
Right.
Then the next step is, based on that, can you physically create entangled superposition qubits to do what you want to do?
Right.
Is it sensing? Right? Is it computing? Is it communicating? Right? But it's not a real thing, but at least in a lab, you got something physical. Right?
Yeah.
It is a physical phenomena, not just a simulation of a physical phenomena. That's level 2. Right? Level 3 is to say, oh, no, I can actually put it, in 20 different places that are separated by, 20 miles. And it kind of works. It's not just in the lab, it's kind of in the field, but it's managed, by 3 universities.
Yeah, right.
Right. I mean, right. So that's like level 3, right? And then level 4 is to say, oh, you want this? Here it is. I'm here to sell it to you. Right? And so I think many times when an ordinary person, when you say ordinary person, a person who reads a newspaper or hears, a news article, they're thinking level 4. Right?
Yeah.
But many papers that are uploaded and press releases put and LinkedIn messages are actually at level 1.
Right.
Okay. So I think that's. In fact, this framework I used to stop the fight between these 2 professors at NAE to say, okay, you're complaining that he's not level 4.
Yeah.
Right? But level 3, while you're trying to push that you're useful, but aren't you just level 2?
Yeah,
Right?
right.
Right. And so at least it got, some of those things done.
Yeah.
In quantum computing, I think it will be largely transparent to a consumer. I think it'll be like an accelerator inside a GPU cluster.
Okay.
That is, you send your requests. Right now, it goes into a hyperscaler. The
Mhm.
hyperscaler sends it out to various, pieces to give you the answer. One of those pieces could be this quantum or quantum
Got it.
inspired thing, right?
Okay.
So it's there, but you don't necessarily see it.
Yeah.
Right. So I think that's how the quantum computing application will come. It'll be inside a hyperscaler, it'll be inside a cluster of compute.
Okay.
Quantum sensing, again, I believe will come more on B2B applications, infrastructure applications.
Yeah.
So again, people who run pipelines and supply chains would be aware of it.
Yeah.
But if you're just a regular person, if you say, I go to the grocery store, what's the consumer product?
Yeah.
Right. So again, to your question, I think you're asking which consumer product
Level 4.
will hit level 4.
Yeah. Yeah.
Right. That I don't know.
Yeah.
I think, honestly, there could be quantum sensing applications already in place by the defense, which you and I are not supposed to know.
Sure.
Right.
Yeah.
Now, after 10 or 20 years, they release a slightly crude version of it to commerce, and then, like the GPS, it becomes, kind of useful commercially.
It sounds like
to
you're
us.
saying for a while we might enjoy the benefits, the downstream benefits of like this is faster, this arrives fresher, right? Like the gas leaks are non-existent, but we won't necessarily hold in our hands products of the second revolution the way we currently hold in our hands
That's right.
products of the first quantum revolution.
Yeah. So I think consumer products, I don't see it as the first scaled use in the world.
That makes a lot of sense. Yeah, especially with the ladder, which is kind of helpful to see.
Yeah.
The levels you have to go up.
Yeah.
So maybe this is sort of related. A lot of public discussion around quantum can sort of feel like we've said sci-fi, right? Bizarre, spooky. Where do you think? Because you're deep in this. We gave people a window into what academic paper or conferences are like. You're deep into this field and talking to other experts. Where do you think the hype currently exceeds the reality? What are maybe people misunderstanding about, in actuality, the state of the second quantum revolution?
I think quantum inspired computing is already here.
Mm-hmm.
So thinking like how a quantum computer would work, but without having a quantum computer in place, and still designing specialized hardware and algorithms to do so, is already here. So I think there is no hype there.
Yeah.
The hype, I think, is when you think about having what is called the fault tolerant quantum computer, which means that it does what it's supposed to do, and it has enough number of qubits, which are a measure of how much information it can keep, and it is able to solve problems you care about substantially faster than what your GPU cluster or a quantum inspired cluster can do. I think that is still many years away.
Yeah.
Okay. Now, of course, if I was in the meeting, somebody in one of those companies like PsyQuantum or somebody would jump up and say, "No, it's not many years away. It is only some years away." Okay,
Yeah.
but nobody will say it's 2026.
Yeah.
Okay,
right.
so I think true fault tolerant quantum computing, depending on who you ask, realistically is at least 5 years away.
Okay.
And I'm being very optimistic over
Yeah.
that. I believe some examples of quantum sensing at the infrastructure level and so on and so forth may be only a year or two away.
Mm-hmm.
Quantum communication is interesting because, to some extent, without something called a quantum repeater, it's already here, but it means that you can't go a lot of distance. Okay. basically the information dies out, and then you need to create something that you know re, re creates it and sends it out. And I don't see the quantum repeaters coming out anytime soon.
Okay.
So my own take as of today is there could be some commercial and defense quantum sensing applications before 2030. Quantum inspired computing is already here. Maybe quantum computing in the 2035 to 2045 range.
Yeah.
And unless there is some kind of a conceptual breakthrough on quantum repeaters, I don't have a timeline for it.
Yeah. You heard it here first. We'll place our bets.
Mm.
So I want to jump now. And this is maybe similar. If the second quantum revolution succeeds, I mean, maybe success is even the wrong word. This is coming. Like you're seeing evidence of it. As this rolls out, if you project out 20, 30, 40 years, how might everyday life look different for people? Where could we could maybe expect they would realistically feel its impact the most strongly, whether that's holding products or whether that's downstream effects from those lower levels you were talking about?
Yeah, first, I think we don't know what we don't know, and we haven't yet imagined, what you can do when something like that comes up, right?
Yeah.
I mean, for the person who invented the integrated circuit, they wouldn't have seen wireless coming, and then they wouldn't have seen somebody say, "Oh, I'll combine GPS with wireless and smartphone and create Uber." I mean, right?
Sure.
I mean, right? How would even a Nobel Prize winner for a technology at at a time T?
Yeah.
I don't think could have predicted how that technology becomes part of some mix-up that goes happen. So my real answer is I actually don't know, because I think it's very hard to imagine how somebody would put these pieces together, right?
Yeah.
But there are some things that you can say seem reasonable to expect, and to some extent, because they're reasonable, they're not sexy. Right? I mean,
Sure.
but it's almost the definition, right?
Yeah.
You don't look and say, "Whoa, what is that?" I mean, right? I mean, right?
Yeah.
I mean, to say, okay, if something takes 10 hours, it's going to take 2 hours. That's cool. I mean,
Yeah.
right?
Right.
And if it means that the number of times my computer gets hacked, reduces,
Yeah.
by 1/10, and
We don't hate it, but it doesn't blow our minds.
it doesn't blow your mind. It
Yeah.
seems like a reasonable extrapolation of things, right?
Yeah.
So going back to, I think, downstream benefits, if people are spending 6 months, 12 months, 18 months to figure out new drug choices for cancer or new materials for so and so, will that speed up the cycle time so that they can do it in 6 days?
Yeah.
Right. Again, it's just the same thing faster, as there's an old poster I have with a woman who drinks coffee and says, "I'm doing the same thing, just faster." Right?
Yeah, right.
So I think in the foreseeable future, people are saying, can you do it more secure? Can you do it faster?
Yeah.
Can you sense things that you cannot sense? Can you look at longer distances that you cannot, right?
Yeah.
So these are all within reasonable extrapolations, right?
Right.
But automatically that means they don't grab you.
Yeah. And
right?
they're within the realm of things we can imagine, but you're saying we have to give space for the whole realm of things we cannot imagine.
That's
that
right.
will probably come to be.
Right.
Well, Dr. Sridhar Tayur, this has been so interesting. Thank you for educating us and talking about your work.
Thank you.
The Tepper Perspectives podcast is made possible in part by the MBA Class of 2016 Technology Fund.